Okay, today's quant question is power to the matrix. So it's a linear algebra question again, because I'm right now doing linear algebra review. So given the matrix A is this thing, find A to the 10th times V, where V is this 3 and 2. The answer is in the form of this thing for integers A, B, C, D, P, G, find whatever this is. So basically we do want to find this, whatever this matrix is. And we see that when we have such a matrix that looks like A to the 10th, um, obviously we're going to have to find the eigenvalue and eigenvector before we can do anything with it. So that's what we're going to do. We're going to want to diagonalize the matrix. So if we want to find the eigenvalue, obviously we have to use determinant A minus lambda I to find the characteristic equation. And we find that lambda is equal to um, 5 and 1 because we got here that this thing was equal to plus or minus 2. So then lambda is equal to 5 and 1. So for lambda equals 5, we want to find the respective eigenvector. So we substitute it back and we get back to this equation and we get this matrix. And then we want to find what x1 and x2 are. So then that's our eigenvector. So this gives negative 2x minus 1, negative 2x x1 plus x2 equals 0. So then our eigenvector is 1, 2. And it's the same for the other eigenvector. We plug it in, so we get this matrix. Then we're trying to find this. So we know that 2x plus 2x1 plus x2 equals 0. So our eigenvector is this thing. Now, once we get these eigenvalue and eigenvector, we kind of have two ways to work around this. The first way is to express V as a combination of the eigenvectors. So we know 3, 2 can be represented in with our eigenvector with some coefficient C1 and some coefficient of C2. So then we find what C1 and C2 are based on this. And we find that C1 is 2, C2 is 1. So then when we apply A to the 10th, A to the 10th is basically just a linear combination of 2 and 1. And since A to the 10th times V1 would just be 2 times 5 to the 10th to the 1, V1 is 1 over 2. And so on and so forth here with 1 to the 10th, because that's the other eigenvector, eigenvalue and its respective eigenvector. So we get this equation. And then obviously in the end, it's just matching the coefficient up, and we just sum it up based on what they need, and we get this value. So I think the difficulty in this approach, I mean, this is pretty straightforward. It's like you have to get the eigenvalue and eigenvector before you can do anything, and then you solve it. I think the difficulty in this approach is just splitting thinking of how to split the V into linear combination of the eigenvectors, but I guess this practice is also pretty standardized. And once you split it up, then it's just combining the coefficient, the eigenvalue, and the vector. And I think the other way that I was thinking of doing this problem was diagonalization. So then I would get it into this formula where I have a diagonal matrix in the middle. I have P and I have P negative 1, like the inverse of P. I think this method makes a lot more sense to me because when we have something of the form P, D, P inverse, if we do it again, if we multiply the same thing, the matrix squared, then like what happens is that this inside here, the P inverse and P would just cancel out to become I, which would just be itself. So then we would just get PD2 D squared. Sorry, my 2 is not looking very good. P inverse. So that's kind of how it works. Is that if we have n power, it would just only be this diagonal matrix, which is very easy to work with. So once we put in the eigenvalue and eigenvector, we get P is this is our diagonal matrix. pretty straightforward. Eigenvectors are here. Our eigenvector is this and this. So what we do next is we have to find the inverse. That's like the bad thing about this approach is that we do have to find the inverse, which is a little annoying. But because it's a 2 times 2, we have a standardized formula, so it's pretty straightforward. 1 over the determinant, which is AD minus BC, and then switch the AD and negate the B and C. And also they have to be swapped a little bit as well. Okay, so then the determinant is just this thing. So then we have the determinant on the bottom of the denominator. We swap the things, swap the diagonals, like the A and D terms, and negate the B and C terms. And we get this. The inverse of P is this. So next we know that A to the 10th is this thing. So then we can just do A to the 10th V is equal to this thing. So then we have to calculate P negative 1, like the P inverse times V. So then we do that calculation, we get 2, 1. Multiply by D to the 10th. Because it's a diagonal matrix, it's so much simpler. We just straight do the exponent on the top. Relatively straightforward. And then we can just multiply it by P and we get our final thing. I think this way makes more sense with the matrices, but I would say this approach is relatively simpler in calculation. Okay, that's enough today.